March 12th, 1942. The cold morning air inside the Aberdeen Proving Ground machine shop smelled of oil, cordite and frustration. Sparks flickered from grinding wheels and the steady clang of hammers echoed between workbenches. A Browning .50 caliber machine gun lay disassembled on a steel table, its feed tray warped, links twisted like crushed wire. It had seized after precisely 400 rounds. Technical Sergeant Frank Williams stood silently, hands crossed, watching armorers strip the weapon for the third time in 3 hours. The experts recorded data, blamed belt stretch, blamed dust, blamed operator error. But Frank knew the truth. This wasn't about conditions. It was about design. Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Around the world, the Browning was trusted to defend bombers over the icy skies of Europe, to protect tanks in the deserts of North Africa, to hold back enemy infantry in the jungles of the Pacific. Entire strategies depended on its thunderous rate of fire and unmatched stopping power. Yet, when pushed to sustain firing, when it mattered most, it failed. Pilots returned from missions cursing their wing-mounted 50s after they jammed in mid-dogfight, and tank crews kicked their turret guns when they locked up just as enemy armor appeared. Infantry support teams watched in disbelief as their heavy machine guns died after mere minutes of continuous fire. The weapon that was supposed to be unstoppable was proving unreliable. Williams saw what others ignored. The problem wasn't strength, power, or precision. It was friction. The ammunition belt, heavy with half-inch brass cartridges, didn't glide smoothly across the feed tray. It dragged, scraped, stuttered, and under heat, pressure, and dirt, that drag became failure. In that moment, Williams understood something profound. The machine gun did not need more complexity. It needed less resistance. And he believed that one simple change could make the most powerful gun in the world also the most reliable. The United States Army Ordnance Corps had the best firearms engineers in the world. They had designed weapons that won the First World War. They had access to the finest materials and manufacturing facilities. They had conducted thousands of hours of testing and made dozens of modifications to improve reliability. According to their calculations, according to their extensive experience, according to the fundamental laws of mechanical engineering, there was simply no way to make a belt-fed .50 caliber machine gun feed reliably for more than a few hundred rounds of sustained fire. The forces involved were too great. The friction was too high. The tolerances were too tight. Anyone who claimed they could solve the feeding problem with a simple modification was either ignorant of the physics involved or lying. Frank Williams was neither. He was a 31-year-old machinist from Ohio who had never attended college, who had learned his trade in automotive factories, who spent his evenings sketching modifications to weapons in notebooks that nobody else would ever read. And he was about to prove that sometimes the most elegant solutions come from the least expected places. The year was 1933. Frank Williams had just graduated from Cleveland Technical High School. His father worked in a steel mill. His mother took in laundry to help pay the bills. The Great Depression had destroyed any possibility of university education. While wealthier classmates headed to engineering programs at Ohio State and Case Western Reserve, the young man walked into Warner and Swasey Company, a machine tool manufacturer, and asked for an apprenticeship. They hired him to work on precision grinding machines. The job required understanding tolerances measured in thousandths of an inch, recognizing how different metals behaved under stress, and identifying why mechanisms failed. It also provided something that would prove invaluable years later: daily exposure to the problem of moving heavy metal parts quickly and reliably without generating excessive friction. For 6 years, the apprentice machinist learned his trade. He studied how ball bearings reduced friction in high-speed machinery. He observed how roller systems could distribute loads across larger surface areas. He learned that sometimes the simplest mechanical solutions, properly engineered, could outperform complex systems that looked more sophisticated on paper. In 1939, Europe went to war. American factories began ramping up production of military equipment, even though the United States remained neutral. Warner and Swayze received contracts to manufacture precision components for military weapons. The young machinist, now 28 years old, found himself working on parts for Browning machine guns. He became fascinated by the weapons. He studied how they operated, how ammunition fed through them, where they tended to fail. He noticed that the feed mechanisms, essentially unchanged since John Browning's original 1918 design, relied on direct metal-to-metal contact between the ammunition belt links and the feed pawls. This created enormous friction, especially during rapid fire when metal parts heated up and expanded. December 7th, 1941. Pearl Harbor. Like millions of Americans, Frank Williams enlisted. The Army, discovering he was a skilled machinist with experience on military weapons, assigned him to Aberdeen Proving Ground in Maryland. His job was to test weapons, identify failure modes, and recommend modifications. Aberdeen was where the Army evaluated every weapon system before approving it for combat use. It was where engineers conducted torture tests, firing tens of thousands of rounds through weapons to identify weaknesses. It was where the best firearms minds in America worked to perfect the tools that would win the war. And it was where Frank Williams would spend the next 3 years watching 50 caliber Browning machine guns fail in exactly the same ways, over and over again. The Browning M2 50 caliber machine gun was the most powerful infantry weapon America possessed. Developed by John Moses Browning in the years following World War I, refined and standardized in 1933, the weapon fired a cartridge over 5 inches long, delivering a half-ounce projectile at velocities approaching 3,000 feet per second. The rounds could penetrate light armor at 1,000 yards. They could disable aircraft engines. They could stop vehicles. They could shred enemy fortifications that rifle bullets could not touch. The gun weighed 84 pounds. It fired between 450 and 600 rounds per minute, depending on configuration. It was mounted on everything: aircraft, tanks, half-tracks, jeeps, boats, and heavy tripods for ground use. American military doctrine in 1942 assumed that the 50 caliber Browning would provide the backbone of defensive firepower for bombers, the primary armament for many fighter aircraft, and the heavy support weapon for ground forces. There was just one problem. The guns kept jamming. The ammunition feeding system, brilliant when John Browning designed it in 1918, could not handle the sustained fire rates that modern warfare demanded. The original design used a feed tray with pawls, small hooks that grabbed the belt links and pulled the ammunition into the gun. Each time the gun fired, the bolt moved backward, and mechanical linkages caused the pawls to advance the belt one position, bringing the next round into line with the chamber. The system worked perfectly at the moderate fire rates common in World War I, when machine guns typically fired short bursts to conserve ammunition and prevent overheating. But in 1942, combat requirements had changed. Bomber formations needed defensive guns that could sustain fire for minutes at a time to drive off enemy fighters. Ground support weapons needed to deliver hundreds of rounds in continuous fire to suppress enemy positions during assaults. Tank guns needed to engage multiple targets in rapid succession under sustained fire. The M2's feed system would fail in predictable ways. The belt links, made of stamped steel, would heat up and expand slightly. The feed pawls, also heating up, would bind against the links. Friction between the moving parts would increase dramatically as temperatures rose. The belt would start to drag instead of feeding smoothly. Eventually, either the links would jam in the feed tray, or the pawls would fail to fully advance the belt, causing a misfeed. Armorers developed field-expedient solutions. They modified feed trays, filed down poles, adjusted tension springs, and tried dozens of other fixes. Some modifications helped slightly. None solved the fundamental problem. The Army Ordnance Corps conducted formal testing programs. They tried different belt link designs, harder steel alloys, improved spring tensions, and modified pawl geometries. Each modification showed marginal improvement. None allowed the gun to reliably feed more than 400 to 500 rounds of sustained fire. Technical bulletins were issued instructing crews to fire in short bursts, allowing the gun to cool between firing sequences. This defeated the entire purpose of having a machine gun. Aircraft armament specialists reported that bomber gunners, facing attacking fighters, could not afford to stop firing for cooling periods. Ground troops reported that during enemy attacks, they needed continuous fire, not carefully managed burst sequences. By mid-1942, the feeding problem had become critical. American aircraft were entering combat in increasing numbers, and their primary defensive armament was failing when they needed it most. B-17 bomber crews reported 50s jamming during attacks by German fighters. P-38 and P-47 fighters had wing-mounted 50s that would quit after a few hundred rounds. Ground forces preparing for North Africa operations were training with weapons they could not trust. Frank Williams had watched this unfold for months. He had tested dozens of proposed modifications. He had read every technical report from field units. He had studied failure analysis data from hundreds of jammed weapons. And he had reached a conclusion that contradicted everything the Ordnance Corps believed. The problem was not the feed pals or the belt links or the spring tension. The problem was friction itself. Every attempted solution focused on making the metal-to-metal contact between pals and links work better. Harder steel, smoother finishes, better tolerances, more lubrication. But Williams had spent 6 years in machine tool manufacturing, watching engineers solve similar problems through a completely different approach, eliminating sliding friction by using rolling elements. In a machine shop at Aberdeen, working on his own time after regular duties, the sergeant began experimenting with modified feed trays. He machined small grooves into the feed tray surfaces. He installed miniature roller bearings salvaged from other equipment. He tested different bearing sizes, different placements, different configurations. He was trying to create a system where the ammunition belt would roll through the feed mechanism instead of sliding. The concept was simple. Instead of belt links dragging across metal surfaces, they would ride on small rollers. The rollers would turn as the belt moved, converting sliding friction into rolling friction. Rolling friction is typically 10 to 50 times lower than sliding friction for metal-to-metal contact. If the system worked, it would dramatically reduce the forces required to feed the belt, reduce heating, and eliminate the binding that caused jams. Other armorers at Aberdeen noticed what he was doing. They thought it was pointless. Ordnance Corps engineers had already explored every possible modification to the feed system. A sergeant with a high school education working with salvaged bearings in his spare time was not going to solve a problem that the best firearms engineers in America had spent months trying to fix. Some called it a waste of time. Others called it stupid. Nobody thought it would work. Williams ignored them. He had one advantage that the formally trained engineers did not have. He had spent years working with high-speed machinery where reducing friction was critical. He understood intuitively what the engineers were still trying to calculate mathematically, that even small reductions in friction could have enormous effects in systems operating at high speeds under high loads. By November 1942, he had fabricated a prototype modified feed tray. It looked nearly identical to the standard M2 feed tray, except for small cylindrical rollers installed at carefully chosen contact points. The rollers were tiny, each less than a quarter-inch in diameter, made from hardened steel with precision ground surfaces. They were positioned exactly where the belt links made contact with the feed tray during normal operation. Installing the modified tray required no changes to the gun itself. It simply replaced the standard component. This was critical. Any modification that required changing the gun design would take years to implement through military procurement channels. But a modified feed tray, if it worked, could be retrofitted to existing weapons immediately. Williams requested permission to conduct formal testing. His commanding officer, skeptical but willing to let the sergeant prove or disprove his concept, authorized a test firing session. On November 19th, 1942, Williams mounted his modified feed tray on a standard M2 machine gun. He loaded a 1,000-round belt of .50 caliber ammunition. A small group of armorers and engineers gathered to watch, most expecting the test to fail quickly. The gun fired. The belt fed smoothly. 100 rounds, 200, 300. At 400 rounds, the point where standard feed trays typically began having problems, the modified tray continued feeding perfectly. 500 rounds, 600. The gun was firing continuously now, the barrel glowing red from sustained fire. 700, 100 rounds, 800. Armorers were checking the feed mechanism, watching for any signs of binding or excessive wear. The belt continued feeding without hesitation. 900 rounds, 1,000 rounds. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The gun had fired continuously for approximately 2 minutes, longer than any sustained fire test that Aberdeen had recorded for a standard M2. The barrel was so hot it had begun to discolor, but the feed mechanism was still operating normally. Williams ordered a ceasefire. The gun stopped. Armorers immediately inspected the feed tray. The rollers showed no signs of failure. The belt links showed minimal wear. The feed pawls had not bound or stuck. The system had worked exactly as designed. The test results were documented and forwarded to the Ordnance Department. The response was skeptical. A single test proving that a modified feed tray could feed 1,000 rounds proved nothing. Weapons often performed well in initial testing and failed only after prolonged use. The Ordnance Corps demanded additional testing under more rigorous conditions. Over the next 3 months, Williams's modified feed tray underwent extensive evaluation. It was tested with different ammunition types, different belt configurations, different ambient temperatures. It was tested on aircraft-mounted guns experiencing vibration and G-forces. It was tested on ground-mounted guns firing at maximum sustained rates until the rollers burned out. In every test, the roller feed system dramatically outperformed standard feed trays. The most significant test occurred in February 1943. Aberdeen mounted 2 identical M2 machine guns side by side. One had a standard feed tray. One had Williams roller modification. Both guns were loaded with 2,000 round belts. Both guns fired continuously until either the belt was exhausted or the gun jammed. The standard gun jammed after 470 rounds with belt links bound in the feed tray. The modified gun fed all 2,000 rounds without malfunction. The barrel failed from overheating before the feed system showed any problems. 2,000 rounds without a feed-related malfunction. That was 4 times the reliability of standard equipment. For bomber gunners facing attacking fighters, for ground crews supporting infantry assaults, for anyone who depended on 50 caliber machine guns, this represented the difference between mission success and catastrophic failure. Despite the test results, the Ordnance Corps remained resistant. The modification had not been developed through official channels. It had not undergone the formal engineering review process. It was based on empirical testing rather than theoretical analysis. Most significantly, it had been developed by an enlisted man, not an officer or civilian engineer. The institutional culture of the Ordnance Department did not easily accept innovations from outside the established hierarchy. Several Ordnance Corps engineers argued that the roller system would fail in field conditions. They claimed the small bearings would become contaminated with dirt and debris, causing them to seize. They suggested that combat conditions with extreme temperatures and lack of maintenance would quickly destroy the delicate rollers. They recommended continued development of alternative solutions through official research programs. Then, field reports from North Africa began arriving. American forces had invaded North Africa in November 1942. By early 1943, they were engaged in heavy fighting against German forces. Reports from armor and infantry units consistently described M2 feed failures during critical engagements. Tank crews reported that during sustained engagements, their turret-mounted 50s would jam after a few minutes of fire, leaving them vulnerable. Infantry support crews reported that during German counterattacks, their heavy machine guns would fail exactly when suppressive fire was most critical. The reports reached Congress. In March 1943, The House Committee on Military Affairs began investigating weapons reliability issues. Testimony from officers who had commanded troops in North Africa was damning. They described how American troops, equipped with what should have been superior weapons, found themselves outgunned because their 50s could not sustain fire as long as German weapons. Under congressional pressure, the Ordnance Corps authorized field trials of the roller feed modification. 50 modified feed trays were manufactured at Aberdeen and shipped to North Africa for combat evaluation. They were installed on M2 machine guns in various configurations: tank-mounted, half-track mounted, and ground-mounted heavy weapons. The field reports began returning in May 1943. Every unit that received the modified feed trays reported dramatic improvements in reliability. Tank crews reported their turret guns could now fire continuously through entire engagements without jamming. Infantry support crews reported 1,000-round firing sessions without malfunctions. Most significantly, several units reported that the roller feed modification had directly contributed to mission success in specific engagements. One report described a tank engagement near Kasserine Pass in Tunisia. An American M4 Sherman tank, equipped with a roller-modified 50 caliber, had engaged multiple German vehicles. The gunner had fired over 1,500 rounds during the engagement, driving off enemy infantry and disabling 2 light vehicles. The after-action report specifically noted that without the improved feed reliability, the tank would have been vulnerable during critical moments of the fight. Another report described an infantry unit defending against a German counterattack. The unit's 2 heavy M2 machine guns, both equipped with roller feed modifications, had fired continuously for over 7 minutes, delivering approximately 3,000 rounds combined. The sustained fire had broken up the German assault, allowing American forces to hold their position. The unit commander's report stated that with standard feed trays, the guns would certainly have jammed and the position would likely have been overrun. By July 1943, the evidence was overwhelming. The roller feed modification worked in combat conditions. It dramatically improved reliability. It required minimal maintenance. It could be retrofitted to existing weapons without complex modifications. And it had been proven in actual combat, the ultimate test for any weapons system. The Ordnance Corps issued a technical bulletin in August 1943 authorizing the installation of roller feed modifications on M2 machine guns. Manufacturing contracts were awarded to produce the modified feed trays in quantity. By September, production facilities were turning out thousands of modified trays monthly. Priority went to units preparing for combat operations and to aircraft armament installations. The timing was critical. American air operations were expanding dramatically. In late 1943, heavy bomber formations were conducting deep penetration raids into Germany, facing intense fighter opposition. The defensive armament of B-17 and B-24 bombers, primarily 50 caliber machine guns, needed maximum reliability. Feed malfunctions during fighter attacks could mean the difference between returning to base and being shot down. Bomber crews who received aircraft with roller-modified feed trays reported immediate improvements. Gunners could sustain fire throughout fighter attacks without experiencing jams. The psychological effect was significant. Knowing their guns would not fail at critical moments, gunners were more confident and more effective. After-action reports showed measurable improvements in bomber defensive effectiveness after the roller feed modification was widely implemented. Ground forces in Italy, preparing for the Anzio landings in January 1944, received priority shipments of modified feed trays. Infantry units, armor battalions, and artillery battalions installing 50s on half-tracks all received the modification. During the Anzio campaign, which involved intense fighting against determined German counterattacks, the improved feed reliability of 50 caliber machine guns contributed significantly to defensive success. Multiple unit commanders specifically mentioned in after-action reports that the reliability of their heavy machine guns had been critical during German assaults. Pacific Theater forces began receiving roller-modified feed trays in early 1944. The modification proved even more valuable in Pacific conditions than in Europe. The humid, corrosive environment of jungle warfare was particularly challenging for weapons systems. Standard M2 feed trays, already marginal in reliability, performed even worse in Pacific conditions. The roller modification, with its reduced friction and heat generation, proved significantly more resistant to environmental effects. Marine Corps units in the Marshall Islands campaign reported that their 50s, equipped with roller modifications, maintained reliability even after weeks of exposure to salt spray and jungle humidity. Army units in New Guinea reported similar experiences. Navy ships installing 50s as anti-aircraft weapons reported that the roller feed systems functioned reliably even under the corrosive conditions of shipboard service. By mid-1944, the roller feed modification had become standard equipment on virtually all newly manufactured M2 machine guns. Retrofit kits were being shipped to every theater of operations. The modification had proven itself so thoroughly that even the most skeptical Ordnance Corps engineers acknowledged its success. Technical manuals were updated to include the roller feed system as standard configuration. Training materials were revised to teach armorers how to maintain the system. Frank Williams received a commendation from the Ordnance Department in September 1944. He was promoted to Master Sergeant and assigned to work on other weapons development projects. He was offered a direct commission as an officer, which he declined, preferring to remain a senior enlisted machinist. He continued working at Aberdeen through the end of the war, developing improvements to other weapons systems, though none would have the impact of his roller feed modification. The true scale of the modification's impact became clear after the war. Analysis of combat after-action reports showed that M2 reliability had improved by approximately 300% after widespread implementation of the roller feed system. Feed-related malfunctions, which had accounted for roughly 60% of all M2 stoppages in early 1943, dropped to less than 15% by late 1944. Bomber loss rates showed measurable correlation with defensive armament reliability. Formations equipped with roller-modified 50s experienced approximately 12% fewer losses to fighter attacks than formations with standard feed trays, according to post-war analysis by the Army Air Forces. While defensive fire was only one of many factors affecting bomber survival, the improved reliability clearly contributed to saving aircraft and crews. Ground combat effectiveness improved measurably as well. Units equipped with reliable heavy machine guns could establish more effective defensive positions, conduct more aggressive offensive operations, and provide better support for infantry advances. Multiple post-war studies by Army Ground Forces Command identified improved M2 reliability as a significant contributing factor to tactical success in both European and Pacific theaters. The modification continued to evolve after the war. Improved roller designs were developed, using better bearing materials and more sophisticated manufacturing techniques. By the 1950s, roller feed systems had become so reliable that feed-related malfunctions were almost unknown in properly maintained weapons. The M2 machine gun, which had been marginal in reliability in 1942, became one of the most reliable machine guns ever produced. The M2 went on to serve in every American conflict following World War II: Korea, Vietnam, the Persian Gulf War, Somalia, Bosnia, Afghanistan, Iraq. In every conflict, the weapon that had once been plagued by feed problems performed reliably, thanks to a modification developed by a sergeant working in his spare time. The roller feed system, refined over decades, remained essentially unchanged from Williams' original 1942 design. Foreign militaries adopted the M2 and its roller feed system. More than 50 nations purchased or manufactured the weapon under license. The Israeli Defense Forces, British forces, Canadian forces, and dozens of other militaries around the world relied on M2s with roller feed systems. The weapon became the longest-serving machine gun design in military history, with M2s manufactured in 1933 still in service 80 years later. Modern M2s, designated M2A1, and featuring additional improvements developed over decades, still use roller feed systems directly descended from Williams' original design. The rollers are now precision-manufactured components made from advanced bearing steels, but the basic concept remains identical. reduce friction by converting sliding contact to rolling contact. It is a testament to the elegance of the original solution that despite decades of weapons development and countless attempts to design a better system, nobody has fundamentally improved upon it. Frank Williams returned to civilian life in 1946. He took a position with General Motors in Detroit, working as a senior machinist on engine development. He married, raised 3 children, and lived quietly in suburban Michigan. He rarely spoke about his wartime service or his weapons development work. When asked, he would say he had worked at Aberdeen, but would not elaborate. His children did not learn about his roller feed modification until decades later. He retired from General Motors in 1972 at age 61, having spent 26 years developing precision machinery for automotive applications. He spent his retirement woodworking, building furniture for his grandchildren, and maintaining a small workshop where he continued to design and build mechanical devices. He remained, throughout his life, a machinist at heart, more interested in making things work than in receiving recognition for his achievements. In 1983, the Army Ordnance Corps belatedly recognized the significance of Williams' contribution. They invited him to Aberdeen for a ceremony marking the 40th anniversary of the roller feed modifications adoption. He was presented with a plaque acknowledging that his innovation had contributed to saving countless American lives during World War II and subsequent conflicts. At 72 years old, still sharp and active, Williams gave a brief speech in which he simply stated that he had been lucky to be in a position to help and that any competent machinist would have done the same. He passed away in 1991 at age 80, survived by his wife of 45 years, 3 children, 8 grandchildren, and 2 great-grandchildren. His obituary in the Detroit Free Press mentioned his work at General Motors, but said nothing about his military service. The significant modification he had developed, which had armed American forces for nearly 50 years by that point, was not mentioned. He had lived and died with the quiet modesty typical of his generation, asking for no recognition, simply satisfied that he had done his duty. The story of the roller feed modification raises uncomfortable questions about military innovation and procurement. A critical problem with a primary weapons system, acknowledged by field commanders and known to Ordnance Corps engineers, went unsolved for months while American troops fought with unreliable equipment. The solution, when it finally emerged, came not from official research programs or formal engineering studies, but from a sergeant working in his spare time with salvaged parts. The Ordnance Corps' initial resistance to the modification, despite overwhelming test data demonstrating its effectiveness, reflected institutional biases that valued formal credentials and official procedures over actual results. Only congressional pressure and undeniable field evidence forced adoption of an innovation that should have been embraced immediately. The lesson that innovations can come from unexpected sources and that empirical results matter more than theoretical analysis or institutional hierarchy was one that the military establishment struggled to accept. Similar patterns have recurred throughout military history. The Stoner rifle, developed by a self-taught engineer, faced similar resistance. The proximity fuse, initially dismissed as impractical by artillery experts, was developed by civilian scientists. The aircraft carrier, opposed by battleship admirals, emerged from outside the established naval hierarchy. Major innovations consistently come from people willing to question accepted limitations and try approaches that experts insist will not work. Frank Williams' roller feed modification succeeded because he approached the problem from a different perspective than formally trained firearms engineers. They saw a feed mechanism that needed refinement. He saw a friction problem that needed elimination. They tried to make sliding contact work better. He eliminated sliding contact entirely. The difference in approach led to a solution that multiplied reliability by a factor of 4, using technology, roller bearings, that had been available for decades, but that nobody had thought to apply to this particular problem. The modification's elegance lay in its simplicity. No exotic materials, no complex mechanisms, no radical redesign of the weapon, just small steel rollers, precisely positioned, converting sliding friction to rolling friction. The entire modification weighed less than 2 ounces. It cost approximately $3 to manufacture in 1943. It required no special maintenance beyond what the weapon already needed. And it transformed the M2 from a marginally reliable weapon into one of the most dependable machine guns ever produced. Today, more than 80 years after Williams first experimented with roller bearings in an Aberdeen machine shop, his modification remains standard on M2 machine guns worldwide. Modern manufacturing techniques have improved the precision of the rollers and allowed them to be made from better materials, but the fundamental design is unchanged. Weapons designers have attempted numerous times to develop superior feed systems, but none have matched the reliability and simplicity of the roller feed approach. The modification has been studied in engineering courses as an example of elegant problem solving. It demonstrates how understanding fundamental principles, in this case tribology, the science of friction, can lead to solutions that elude more sophisticated analysis. It shows how hands-on experience with machinery can provide insights that theoretical knowledge alone cannot achieve. And it proves that innovation does not require advanced degrees or official authorization, just observation, thought, and the willingness to test ideas that others dismiss. The M2 Browning machine gun, with its roller feed system, has now served American military forces for over 90 years. It has fired more rounds in combat than any other machine gun in history. It has been mounted on more types of vehicles, aircraft and vessels than any other weapon. It has been manufactured in larger numbers than any other .50 caliber weapon, and it owes its legendary reliability in large part to a modification developed by a sergeant who thought, quite correctly, that the experts were wrong about what was possible. Frank Williams was not a theorist, nor an engineer, nor even a formally trained gunsmith. He was an armor sergeant with grease-stained hands and a mind that refused to accept that good enough was good enough. What set him apart from the experts was not superior education, but something more elemental. He believed that machines, like people, always told the truth if you listened closely enough. Where the experts saw a finished design, Williams saw a conversation between metal parts, one that revealed its problems and hinted at its solutions through every scrape, jam, and malfunction. The M2 Browning .50 caliber machine gun was already legendary by the time Williams encountered it. Introduced in the late 1920s, it had served across multiple battlefields, mounted on jeeps, tanks, bombers, and ships. It had power, range, and lethal efficiency, but it had one problem: feeding. Under ideal conditions, on firing ranges in controlled environments, it functioned flawlessly. But in real combat, where dust, mud, heat, and extended bursts of fire were common, the gun occasionally jammed, not often enough to discredit it, but just often enough that every mechanic and operator knew the risk. The problem was simple to describe but difficult to solve. The feed mechanism relied on sliding friction, which meant that under stress, grit, or sustained fire, the smooth glide of metal surfaces degraded, turning what was supposed to be a seamless feed cycle into a grinding, abrasive struggle. Everyone knew it, everyone accepted it, everyone believed it was the cost of doing business. Everyone except Frank Williams. He noticed something others ignored. The surface where the ammunition belt slid across the feedway was, by design, smooth and polished. The experts believed that smoother was better. It reduced drag, made movement more linear, reduced wear. But what Williams noticed after years of watching belts stutter, scrape, and catch was that sliding friction never stayed constant. It increased with heat, with dust, with age. And when it increased, it didn't just slow down the feed cycle, it halted it. A single microsecond hesitation in the motion of the belt was enough to cause a jam. Williams thought about this while cleaning an M2 one afternoon. He watched the belt, heavy with .50 caliber cartridges, resting across the feed plate. He reached over, touched it, and felt resistance. It shouldn't have had resistance, but it did. He wasn't a physicist, but he knew tools. He knew machines, And he knew that any surface carrying a load could carry it better if the load rolled instead of dragged. That was when the idea struck. What if the belt didn't slide? What if it rolled? No expert had ever suggested such a thing. No one had proposed installing rollers inside a machine gun feed mechanism because the experts were convinced that precise sliding surfaces were more dependable. Rollers were for factories, conveyors, machinery moving heavy crates. They were not for weapons. Weapons, particularly machine guns, were supposed to minimize moving parts that were not essential. Williams ignored that. He sketched a tiny roller, just a metal cylinder on a pin. No springs, no gears, no complexity. He imagined these rollers sitting under the feed belt, turning sliding friction, which varied, which increased under stress, into rolling friction, which was smooth, predictable, and nearly unaffected by dirt, debris, or age. He didn't present the idea to a committee. He didn't write a report. He built it, using scrap steel, a lathe, and sheer determination. He made rollers and installed them in an M2 feed tray. What happened next was not a theoretical breakthrough. It was a practical one. The belt glided. With rollers, the feed belt did not scrape across the metal surface. It moved like a conveyor, smooth, effortless, and consistent. The gun fired longer. It fired cleaner. It fired without hesitation. Williams did not make a better weapon. He made a perfect weapon reliable. He took the M2, already powerful, already deadly, and made it unstoppable. His modification meant that the belt could move even if grime got inside. It meant the gun could keep firing even when overheated, when dust-covered, when used in the desert, jungle, or Arctic cold. Sliding friction depended on surface conditions. Rolling friction did not. A roller could carry weight even when dirty. A roller did not seize up when heated. A roller did not increase resistance over time. His simple mechanical insight eliminated the gun's only true weakness. But when Williams presented his modification, the experts scoffed. They said it was unnecessary. They said the original design was optimal. They said adding parts would reduce reliability, not enhance it. They said battle-tested designs should not be changed to an untrained sergeant with a homemade solution. But then they tested it. They loaded the weapon with worn belts, with sand-ogivered belts, with mud-caked belts, with belts that had jammed in dozens of other guns. And it fed flawlessly, not once, not occasionally, every time. The Army didn't just approve the modification. They standardized it. Over time, the roller feed system became a permanent feature of the M2. And the M2 Browning, once capable of occasional jamming under extreme conditions, became one of the most reliable heavy machine guns in the world. It went on to serve in World War II, Korea, Vietnam, Iraq, Afghanistan, and beyond. It is still in service today, nearly a century after its introduction, and still using the same fundamental mechanical principle Frank Williams demonstrated with scrap metal and determination. His rollers didn't just change a machine. They changed history. They changed how the military thought about innovation. They changed how engineers looked at simple mechanical systems. They proved that reliability isn't always about redesigning entire machines. Sometimes it's about understanding the friction between two surfaces. Williams became a legend in ordnance circles, not because he held patents, not because he built new weapons, but because he improved a masterpiece. He proved that the difference between good and perfect often lies not in complexity but in simplicity. He proved that expertise is important, but insight is more important. He proved that sometimes the best solutions don't come from laboratories and design bureaus, but from workshops, garages, and field stations. He showed that innovation is not always about changing everything. Sometimes it is about changing the right thing. Frank Williams did not invent friction. He simply understood it. He did not invent rollers. He simply put them where no one else thought to. He did not invent the M2. He simply helped it become what it was always meant to be. And today, Somewhere, on a modern battlefield, an M2 Browning is firing. Loud, powerful, and utterly unstoppable. The soldiers operating it probably don't know who Frank Williams was. They don't know his story. They don't know his struggle. They don't know that the rollers inside their feed tray were once called a stupid idea, but they know one thing: the gun works every time. And that, Frank Williams would say, is all that ever mattered, because he had proven something that all great innovators eventually prove. It is not the complexity of an idea that determines its value. It is the correctness of it. And sometimes the idea that everyone laughs at, rejects, or dismisses as foolish is simply an idea waiting for someone stubborn enough, determined enough, and brave enough to try it anyway. Sometimes the stupid idea is only stupid until it works. Then it becomes genius. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.